www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So this is 606 solid state devices. If this is the course for which you are in, then you are in the right room. Now, I'm Muhammad Ashraful Alam, and I'm a professor of electrical engineering. And I have been teaching this course for several years now. I have come after a long industrial experience at Bell Laboratories for about 10 years. And so I have a broad industrial background. And I have been teaching it for a few years now, 3-4 years now. And so this is one of the courses that defines sort of the language by which people in our area, microelectronics nanotechnology area, they communicate with each other, because many of you come from different backgrounds. Some from electrical engineering, some from physics, some from different countries. And you will meet here. This course will define the language. And then, of course, in your PhD or master's thesis, you will be doing different things. And this sort of will define the broad framework of how you will discuss these topics among yourselves later on. And most important, there are 2 additional reasons why you take this course. One is this qualifying exam. People say that this is something this qualifying exam is based on, or you'll have to take this course. And the other is when you have job interviews, almost invariably, they will not ask you for any advanced courses. Only thing they will ask you is what you learned in this course alone. So therefore, this is a very important course, both from intellectual perspective and also from practical career perspective. Okay. So let me begin by giving you some broad course information, and then we will go through the other topics of the day. The books, the 2 books we'll be using, these are Advanced Semiconductor Fundamentals. This will be for first 5 weeks. And the second book is Semiconductor Device Fundamentals. This will be for the next 10 weeks. So the first 5 weeks, we'll talk about the basics, the fundamentals, quantum mechanics, statistical mechanics, transport theory. These are general things. Now, in the next 5 weeks or next 10 weeks, we'll apply this, whatever we have learned, the basic equations we have learned, and we'll be applying them to understand how semiconductor devices work, like diode, bipolar transistor, MOSFET, how they work. Now, these 2 things, what we'll do in the first 5 weeks, you'll see we'll go through a lot of things. But at the end, we'll encapsulate it only a very few concepts, 3 or 4 concepts. And that encapsulation would allow us to then explore such complicated devices. These are very complicated things, diode, bipolar, and MOSFET, but in a very simple way. And that is the essence of these 2 books. Now, the course website will be at this cobweb.ecn.purdue at E606. Notice the tilde. And the office hours, as I said, I'll be available after the class, which is supposed to end at 8:20 till 9:15. Either here, we'll stay here as long as possible, and then I'll be available in my office. Office is at EE320, upstairs. Now, in terms of the bad things, which is the homeworks and exams, there'll be 9 homeworks posted, 4 will be graded, and this 4 will be randomly chosen. And there'll be 3 exams as this is the first part of the basic transport theory. After we finish that, we'll have 1 exam. And the second will be after we finish the bipolar transistors. And the third is the final, which we'll do when we have discussed MOSFET. Now, let's get a bird's eye view of what this course is about. And this course essentially has, let me first explain to you that if you wanted to understand a modern electronic device like that computer you have on the left-hand side, then you understand it's a very complex thing. It has lots of ICs, it has a lot of the display itself, has millions of transistors, thin film transistors in the display. The microprocessor sits underneath the keyboard, the hard disk drive, there's ICs for those, analog, digital, all sorts of complicated things. But regardless of what the final product is, it always starts in the foundation of physics. And that foundation of physics is in quantum mechanics, as in statistical mechanics. And when you combine these two, and I'll explain what we mean by this as we go on. Now these two, when you combine them, we'll get something called a transport theory, that when you apply an electric field, then how the electrons move in a semiconductor. If you put excess electron hole pair in some place, how they diffuse away from that point. So this is the basic that creates the foundation. And that's the first 5 weeks, right? The first book, first 5 weeks. Now, once you know how electrons respond as a function of the density gradient, more density one place, less density another place, how they diffuse away, or how they respond in presence of electric field, then you are ready to talk about how different devices work. For example, how resistors work, how semiconductor diode work. These terms you may have heard from your undergraduate years, bipolar and how metal MOSFET works. So this would be the foundation on the right-hand side, and the middle column, this would be the devices that we'll think about. Once you know how these individual components work, that's not the end, of course. Then you will have one transistor, one diode. That's good for nothing. These days, in a microprocessor, you have at least 1 billion transistors. So there are, of course, additional issues. And the additional issues are, of course, how to connect them together, how to make them work as an aggregate. And this would be thin film transistor for the display. As I mentioned, the display on your computer, on the back plane, millions of transistors, almost as large as a microprocessor. Then, of course, you have the microprocessors, you have disk drives that reads of your data, and then there are MEMS for the read heads. So all sorts of other things that you can get by combining the basic devices, right? And finally, of course, you have when you put them together, you have a system. So what is 606? 606 is this rightmost two columns. This is 606, and as you go through your graduate education, you will do the third and the fourth column by other courses, right? So that's what we are after. So what other courses? Well, this is how in Purdue things are arranged. In Purdue, we have the 606 and 604. These are in our area, which is microelectronics and nanotechnology area, are two basic courses. You know, no matter where you come from, whatever your background is, you start with sort of these two courses provides you a foundation. But of course, this is a foundation which is not deep enough for graduate school. This is deep enough for probably undergraduate students. Now, for the first 5 weeks, remember, we said quantum mechanics, statistical mechanics, the transport theory, right? We said that's the first 5 weeks. If you wanted to know more, especially people doing work on the theory and modeling area, then in that case, you will have to take a whole other set of courses, like 656. This is a transport theory, semi-classical transport theory. 659, quantum transport theory. These are transport theory, expanded version of the first 5 weeks. Now, you can take all these courses for the foundation, but those who would be doing, let's say, more experiment or systems, then they would go to the other side, which is the next 10 weeks, right? And then they will go to the system side. And then at Purdue, you have excellent set of other courses. For example, the 654. This is this should be 654 is solid state 2, or this may have a slightly different name here. Solid state 2 is a more advanced version where, you know, whatever you have learned, the basics of bipolar, you will learn about lasers, you will learn about microwave transistors, more advanced devices. But if you know 606 well, this course well, you see, that shouldn't be a problem. You should very easily be able to learn the other material. 612, remember the last 3 or 4 weeks we'll be talking about MOSFET. 612 is essentially all about MOSFET and also bipolar transistor, but that you can take in a more advanced and expanded form in 612. And then there are courses on system design and other issues that you will be able to take, and you should take depending on your interest. But then that gives you the context that if you understand 606 well, then you can see that will create a foundation for all the other courses that you will be taking subsequently. So this is very important, right? Now, that's all about courses. But let me explain to you first that why this course, apart from the requirement, 606 is a required course, but why electronics now is a very exciting place to be, or a topic to learn. You know, last century, people say that this was a century of electronics and started from this radio transmission across Atlantic, great achievement, you know, people even though it takes weeks to go cross the Atlantic in ships, but you could cross the Atlantic in seconds by, if even less, by radio waves. And you know where electronics have come today. But you might not have realized that this 100 years is actually, there was a series of revolutions that happened. And these revolutions are based on electronic devices. And these were very fundamental. It may or may not have happened. And if it didn't happen, then we wouldn't be where we are today in terms of electronics industry. Now, this one on the left side, from 1906 to 1950s, is vacuum tube diode. Even these days, you have vacuum tube diodes in very high power electronics. Okay. Then 1947 onward, you can see that transistor, and by the end of the course, you will know exactly why the transistor has this wedge-shaped form and how it functions. And that was the next 30 years. And then there is this MOSFET from 1960s onward, and that is what we still have in our microprocessors today, right? Now each one of them, each of the transitions, of course, were noted or distinguished by several Nobel Prizes. So these were big things. This is a lot of interesting things. And what I'd like to convince you today, that there are several Nobel Prizes waiting to happen. So maybe one of you. So as this one also comes to an end, the MOSFET, the physics of the time of MOSFET is also coming to some sort of saturation, and we have a great opportunity for the future. So why did this transition occur? That you need to understand. The transition occurred because initially you have one vacuum tube. Well, you have some power dissipation as you hook up with the battery. But very soon, by the end of Second World War, when you put the vacuum tubes together in the system, it looked like that a huge amount of them were failing because it used to be so hot that they used to say that 1/3 of the American Navy during Second World War was in for repair because of some form of failure, and electronic failure was often a big deal. Because when you have a racks full of diodes, so hot that any of them, it's like light bulbs, any of them can fail at any time. And when one fails, you have to take it out, replace it, a big problem. So the power dissipation, when it became so high, the temperature became so high, you couldn't have vacuum tube electronics go any further. So then came the bipolar transistor, and it immediately brought down the temperature because it works at lower voltage. You can put them more together, closer together. take away the power, power came down. But then, of course, what happened is, you cram more and more and more. And by 1980s, the supercomputers had to put in water in order to take away the heat. You could see, literally see, and this I have seen in Cray 2. These were the supercomputer that bubbles are essentially coming out. It's so hot. And of course, therefore, the days of bipolar transistors was gone. And then you had to do it MOSFET. And I don't have to tell you that MOSFET is also getting hotter. Laptops, they sell in Walmart special holders so that it can take your heat out. So laptop is also getting too hot. And think about all the data centers that Google and other people have. Huge power dissipation. And this cannot continue. And so the question is that what is next? So what this course does actually is try to understand this history of 100 years, the essence of this 100 years in essentially 14 weeks, and then try to set you up to see for the next generation. And that's what you are here for, right? You want to do research, you want to work on different topics, and there are many new things. People are talking about spintronics, biosensing displays, wall-mounted displays, that's like a paper, thin sheet of paper, all sorts of things. But if you understand how the previous generation worked, what their problems were, then you are ready to take the next step. So that's what 606 is, a physics of the last 3 generations. Okay? Now, let's start by thinking about the current flow in semiconductors. I have a green region here, which is a semiconducting region, or some conductor. It could be metallic also. 2 contacts, and I have applied a voltage. And you know what will happen, that current will flow. Now, current flows, let's say the electrons shown here in red, flows in one direction, and corresponding current goes in the other direction. Why? Because electron has negative charge. So whichever direction it goes, the current goes the other way. Now, of course, this depends on how much current will go, depends on the resistivity of the material. Now, different materials have different resistivity. So that, of course, depends on the chemical composition, crystal structure, temperature, and doping, all sorts of things. And we'll discuss that in a little bit. Now, one thing is we could make a huge, humongous table, measure the resistivity of every material, and that is, in fact, up till 1900s, that's what people used to do. Ohm's law, they used to make a resistance table of a huge amount of material, just go in the lab, make measurements, and then you are done. But the thing is that only works for known material. If you wanted to try out something slightly different, then, of course, it's better to have a theory for it, that why resistance changes as a function of composition or materials in a particular way. So that would be better, rather than making a big table. Then we won't have to carry a big table with us. Now, as you know, the current through Ohm's law, current is proportional to the voltage. But the other way you could express current, you could say the current involves a certain amount of charge cube. N is the carrier density, however number of carriers you have, multiplied by the velocity, the rate at which they are moving from one point to another. And A is the cross-sectional area. Now, what we will do in this course in first 5 weeks is that first, for essentially 2 or 3 weeks, we'll talk about the physics of carrier density. How do I compute as a function of materials and material structure? How do I calculate the number of electrons I have available for conduction? And that will involve quantum mechanics and equilibrium statistical mechanics. And that's chapter 1 through 4. That's the 1 through 4 of the first book we are talking about. The first book has probably 6 chapters. And the next 2 chapters, the remaining 2 chapters, will talk about how, when you apply an electric field, or if you have density gradient, high density here, low density on the other side, what rate or how fast do the electrons move? That will be the next two chapters, which is chapter 5 and 6, and that's the transport theory. We'll think about scattering as the electrons go along, how they scatter with the lattice, how they scatter with other impurities around. That we will talk about in. And our ultimate goal will be a drift diffusion theory, which I'll explain. And that will, the whole thing we'll use to understand diodes, bipolar transistor, MOSFET. So that's it, right? First 4 chapters, calculating carrier density N, and last 2 chapters, calculating velocity. You're done. Now, the main thing is that, quantum mechanics and statistical mechanics seems like a very complicated thing, but what will be amazing that you will see just 2 concepts. One is this effective mass, and another is something called a Fermi factor. These 2 will be sufficient. After reading all this, that is the 2 things we will carry over. And similarly for transport, all we will carry over is a notion of a mobility and a diffusion coefficient. So we'll do all this, but at the end, carry over only a very few things for our next stage. And we'll explain why such a few things describe such a complicated problem so well. Okay. So let's talk about the 3 things that determine the carrier density. One is this atomic composition, arrangement of the atoms, and for periodic arrays like crystals, the concepts of unit cells and how they are classified. So different types of material systems. So of course we understand that carrier density could be different depending on number of electrons you have in a material. Like silicon have a certain number of electrons, and then let's say copper has a different number of electrons. So the electrons could be different depending on the number of the material, original material you have. And so let's start there. So this is a truncated periodic table. For electrical engineers, for us, our periodic table used to be historically just silicon, nothing else. But it's a little bit expanded version of the periodic table, and you can see the materials of interest. What are the materials of interest? Like from group 4, you see in the middle, from the group 4, materials like silicon is of course very important, and carbon. Carbon in the form of graphene, you may have heard, silicon, carbon nanotube. This type of materials are of great interest for electronics industry, right? So the group 4, and the first transistor was made of germanium. And at the end of the lecture, end of the semester, make sure you know why it was germanium, not silicon. And we should be able to answer that question. Then there are also combinations of group 4 materials that are also huge in significant use. For example, all your microprocessors, the IC in your microprocessors in Pentium, these days have silicon germanium, and you can find them 14 and 32 in the middle column, both of them. And also for high temperature electronics, many times for space shuttles and other things, silicon carbide is a material of great interest. Now, there are also materials, this you might know, from 3 and 5, from column 3 and column 5, like indium phosphide, gallium arsenide, and so on and so forth. Every time you talk in your phone, then the optical fiber carry the signal, and the laser that sends the light through that optical fiber are made of indium phosphide. That used to be red laser is gallium arsenide based, but the indium phosphide, all telecommunication lasers are indium phosphide based. You can also have a more exotic combination like indium, gallium, arsenic phosphide, and again from 3 and 5, from group 3 and group 5. And this, of course, each one of them have different properties. We'll get to that a little later. Now, from 2, 6, you have cadmium telluride. From 2 and 6, you have cadmium telluride. Do you see cadmium? That's 48 on the left side and 52 on the rightmost column, you can see. And the lead sulfide, well, this was the first when the transmission, transatlantic transmission of radio signals. The first diodes they used to have, these are all based on lead sulfide. This is a yellow paste that used to have this rectifying properties. So the first transistors are all based on lead sulfide. It's a very soft material. Now, of course, all combinations are not possible. If you like to put anything in any combination, it is not possible because of lattice mismatch, that all materials do not have the same spacing among the lattice. So you cannot just put them anything with anything else. And you have to think about, people spend their lifetime in terms of developing this material. You know, that's what material science department is for. Now, that's material. But more important or equally important to material is the arrangement of atoms. And the arrangement of the atoms are in solid crystals. The atoms are in specific positions and with specific orientation. Now, it is possible to have specific positions, but random orientation, that's like in plastic crystal, doesn't conduct as well. N you'll be seeing N is significantly lower compared to solid crystals. Then there are these liquid crystals, as I mentioned, the displays, where you have the orientational order, but no positional order. Do you see this? These are in random places. And for liquid, you have neither positional order nor orientational order. And this fourth one doesn't carry too much current. So available number of electrons you will see is very few. On the other hand, for solid crystals, it is significantly more. So order is very important, both orientational and positional order. Now, in addition of this type of division, there are this type of divisions here. This is a cross section of a MOSFET, and we'll talk about MOSFET much later. But I just wanted to illustrate a point. Look at the bottom side on the silicon substrate. These are individual atoms of silicon. Look at them just. Everybody in their place. This is how perfect modern processing is. You have billions of these transistors and almost this perfect throughout your entire IC. Now, that's crystalline. We use a lot, and I'll explain why, the polysilicon gate. And the polysilicon is polycrystalline silicon, where you have crystalline domains of different order. That's one type of material that we should be talking about. The other material, which is like a liquid in terms of random orientation, is this amorphous oxide. And without this, the modern electronics would be impossible. And third one is, of course, the crystalline semiconductor, ordered nice arrays. Now, how do we think about, let's start with crystalline semiconductors, well ordered, and try to define them. But what I want to point out, we do it because it is easy. But at the end, it is not the whole story, of course, but many of the conclusion we'll be reaching based on understanding the crystalline semiconductor, they will apply to amorphous silicon, they will apply to polycrystalline silicon. And I'll explain why. But the point is, we are sort of solving this because it's easy to solve, not because this is the main story. You see? So let's talk about crystalline semiconductor and classification of crystals. So this is a periodic array of points. It could be ions, it could be atomic ions, for example, or for this matter here, for this case, just assume that these are geometrical points, a series of array of geometrical points. Shown here in 2D, it could also be in 3 dimension in periodic array. Now, how will you build it up? It's an infinite array, so one way to build it up is to have a unit motif of a rectangle shown here in yellow, and you can see 1/4 of the corners is included, of each point is included in the yellow. And this you can see that you can repeat and build up the whole crystal. Possible, right? You can just repeat them. But you can also see that this is not unique. You could start something like this, which has the same volume or same area. Do you see that? Because say trapezoid, height multiplied by the base, and it's the same as before. So this is an equivalent description, and you could also use this one to build up the whole crystal. That's possible. You could even do this. You could take one in the center, put a rectangle around, repeat this. Then you can build up the whole system, right? So this motif, if you study the property of any one of them, we will see that is sufficient to understand the property of the whole crystal. That's why we'll be talking so much about the crystalline order or unit cells. That's the amazing thing. Think about a semiconductor that may have, let's say, 10 to the power 23 atoms. Impossible to solve a quantum mechanical problem with 10 to the power 23 atoms, right? We shouldn't even try. No computer in the whole world can solve that many atoms, problems with that many atoms. But what is amazing is that if we can just solve one and patch it up in the right way, we'll see we can have the solution for the whole thing. And that's the power of the unit cell, and that's why we'll be spending a few moments on thinking about the unit cell, you see? Now, of course, unit cell need not be primitive, meaning the smallest volume. It could be something big, and you could also repeat that the blue square, and if you use that same motif, you could figure out the rest of the things. So I think I have just discussed that the unit cells are not unique. You know, you can have various variation of it. It's primitive and non-primitive. Primitive means the smallest one, but even for the primitive one, you can see the yellow one, the trapezoidal one, or one that has the atom in the center. All three are primitive cells, but they are of different types. So even the primitive cells need not be unique. And the property of one, as I mentioned, defines the property of the whole. And that's why we want to understand them in some detail. Now, one very good way, so because it can be done, the primitive cells can be done in various ways, one prescription that you can follow over and over again is something called a Wigner site cell. So this is a way of defining the primitive cell, one of them, but you know, you are fine. If you define one, that's fine. And this is how it works. Choose a reference atom. So these are set of atoms shown here in blue circles. Choose a reference atom, that's the red one in the center. Then the second step is connect to all these neighbors. So by straight lines. So you see here the blue, the red has been connected to the blue, and do that for all of them. Everybody, however you want in the neighbor, first neighbor, second neighbor, whatever you want. Connect them all with straight lines. But of course, you have to take care of all the nearest neighbors. Then, in the next step, you see, you should draw lines which is a perpendicular bisector of the connected lines. So here, the red and a blue on the left side, you see I have drawn a vertical line which is a perpendicular bisector for that line, right? And then you should do it for all the connected lines, all of them. Now you can see the atoms that are farther away, the intersected points, the bisector happens at a point which is farther down. And primitive cell, well, primitive cell is the smallest volume enclosed in this area. So you see the one that happens in the farther out, which is the sort of the right top blue point, the perpendicular bisector is farther out. So when you take second or third or fourth nearest neighbor, connecting them doesn't really affect your primitive cell. So you can take them, but it doesn't really matter. But this would be the primitive cell. So you can you realize that in the previous slide, when you had the atom in the center and the square around it, that was the Wigner site primitive cell. Now now we know about unit cells, the basic definition. Let's say how we can construct different lattices. So one particular structure I have shown here has a lattice constant of A and B, a lattice separation in the vertical direction A, and the other is B. And we'll see how many different ways we can arrange this A and B in order to make crystals, and the angle in between. So that is the definition of a Brevard lattice. So for example, the first definition, let me step back. The first definition is that Brevard lattice is that if you stand on any of the atoms in the lattice, your environment around it should look exactly the same. So for example, if you sit on the one that has the crosses in it, all the neighbors around it should look exactly the same. And I'll give you examples in a little bit later. So that's one definition of Brevard lattice. The other definition is that you should be able to go from any atom, right, any point, to any other point by this multiplying this unit vectors, which is A and B, you know, the sides, the two sides, multiplying it with factors h and k, which are integers. So for example, the one vector that I show, what is the value of h? I have 1, 2, 3, 4. So h is 4 and k is 2 because it goes vertically up. You cannot have 4.32 or you cannot have k equals like 2.5. You cannot have that. It has to be integer values, and by providing the integer values, you should be able to go to any points in the lattice. Now what about this? Is it a Brevard lattice according to this definition? Well, it is not, for this very simple reason, is because you see, if you sit on the yellow atoms, then if you take to the right, you have the green atoms very close by, but on the left, but for the green atoms, you see, there's nothing, not a yellow atom on the right that looks exactly the same. There's a yellow atom on the left, of course, that's exactly the same. So this is not a Brevard lattice, because in Brevard lattice, remember, what is the definition? Every position that you want that the environment should look exactly the same. It doesn't look so. But you can convert it to Brevard lattice by combining the yellow and green into one point. And then you can see, if you sit on the blue points, then the entire environment is the same. But within each blue point, there is this blue and there is this green and yellow subatomic structure. That is the basis. So then you multiply the lattice with the basis, you get actual lattice structure. So in 1D, one dimension, you can see from the top, you have atoms, periodic series of atoms. That's the Wigner site cell, right? And how many you have? In 1D, you have just one type. Because you have a line, you just cut it in the middle, you will just have 1D. And many systems are actually one-dimensional. And these are, of course, in recent days, problems of great interest. Many chemical molecules, polymers, are actually one-dimensional chain. And in that case, like the DNA would be a one-dimensional chain in some effective way, and you can assign a basis and you can then expand it out. So my main point I want to make that in 1D, there's only one type of Brevard lattice, right? What about 2D? Will be more, right? Because 2D has two sides, A and B, and the angle in between. So there'll be more. And it turns out there are exactly 5. In 2D, there are exactly 5, and these are the 5. If the two sides are the same and the angle between is 90 degrees, then that's one type. And two sides the same, angle not equal to 90 degrees, you have a second type. Two sides unequal, angle 90 degrees. Two sides unequal, angle not equal to 90 degrees, and the general form. And you can see the square in the blue. What is that? That's the Wigner site cell for 2D. And you should convince yourself that this indeed is a Wigner site cell. You say, we take the neighbors, bisect the connecting lines, and that would be my Wigner site cell. But main point is 5 types, no more than 5 types, and these would be basis of many, many work. Now, this is an example. This is again not a Brevard lattice. Very important material. This is silicon graphene, a material of great research and a lot of interesting work these days. Maybe some of you already work on this topic. This is again not a Brevard lattice, because if you sit on the yellow, then the blue is on the right. But if you sit on the blue, there's no corresponding yellow on the right. There's a yellow on the left. So this is not a Bravais lattice because it's not equivalent. All points are not equivalent, but you could make it equivalent by doing this. By combining A and B into bases, replacing them with one point, and if you combine all the yellow and the blue in one point, you can see that this will become a rhombus-like structure if you connect them. And that will again become one of the 5 Bravais lattices, right? So that's something you should convince yourself that this indeed is the case. Now, many of these things that you see in classical tiling, these are all can be easily converted into Bravais lattices. You can see for the Kepler tiling, if you put the green one and then bisect all the neighbors with squares, then you can have a square region, which would be a unit cell of a Bravais lattice, and that you could repeat. So obviously, this would be a Bravais lattice with a basis based on that, whatever is inside the green region. But there are many modern materials. I mean, many people make the mistake in assuming that all modern materials must be described by these 5 types. It's not really. It's only when you have one type of motif periodically repeated, then, of course, there are 5 types. But if somebody allows you 2 types or 3, then there are many more materials that can happen. So, for example, these are called Penrose tiles, and you can see that the green one is a little rhombus, and the blue ones are a slightly different rhombus, almost like a square. By putting this together, you can cover the whole surface. It's not periodic, but essentially it's almost periodic. And because now you have 2 types of unit cells, if you allow 2 on the right hand side, if you allow 3 or 4, then you can have many more types. And so the point I wanted to make, yes, not if you see a lattice, which is not a Bravais lattice, you shouldn't automatically think that if I just combine some atoms in some random way, I'll always get back to Bravais lattice. Bravais lattice is very important. It describes a huge number of materials, but that's not the whole universe. There are lots of other materials also that do not follow in the Bravais lattice and cannot be reduced to one, you see? And there are important materials. In fact, people didn't know its existence until 1986. And then all of a sudden, a research group first publishes a result that of material of that type of structure. Nobody believes them in the beginning, and then others start finding it. So it's almost less than 25 years old, the existence of many of this material. What about 3D? Well, life is getting more complicated. 1D, 1, 2D, 5. Well, in 3D, I have 14. So 14, let's start with the top row. 14 you can understand because there are 3 lattice vectors, right? Height, width, and the length. And the angle, pair of angles in between. Of course, there will be more. So you can see, starting from the top, the triclinic has this alpha, beta, and gamma. These are the 3 pairs of 3 angles among a pair of lattice vectors. None of them are equal to 90 degrees. So that's the most general form. Then you can have cubic, all 3 sides the same, angles 90 degree, no problem. Tetragonal, and you can see the 2 sides are the same, the base is the same, height isn't, the height is a little longer, and then onward you have. Now why this 7? This 7 is associated with the rotation angle or various symmetry operation. You can see, you can take a cube, rotate it 90 degree, it will exactly remain a cube, right? Rotate another 90 degrees, so you can exactly have a cube. But you can see, and you can do this vertically also. If you rotate on the vertically, then again you have a symmetry operation. But you can see in a tetragonal one, yes, rotating is sidewise is fine, along a vertical axis is fine. But if you try to rotate it on the horizontal axis, around the horizontal axis, when you rotate 90 degrees, it's no longer the same, right? And so it will look different. So therefore, these whole classification, the 7, people spend their life on, in fact, of how to define these things. Then there are 7. But in addition, if you go vertically along the line, let's go on the cubic, the second column, You will see that there are possibilities where electrons are, or the atoms are only in the corner. That's a normal cubic. Then in the second one, marked as I, there's one atom in the middle of the body. That's body-centered cubic. Makes sense, right? One atom in the body. And the third one is face-centered cubic, because there are 6 faces and you have one atom in all the 6 faces. So that's the face-centered cubic. Now, if you think about it, this is 4 in the vertical column and 7 in the horizontal column. How many there should have been? 28, right? But you can see that there is 14. And there are also lots of blank white spaces. Why did that happen? Why are these blank spaces? So for example, let's focus on this tetragonal one. The third element, there is no face-centered cubic on the tetragonal one, but there is a cubic face-centered. That element is there. Why not? Because it turns out that the second and the third element, the body-centered and face-centered, are exactly the same. So you are double counting. And let me explain why in the next slide. But in order to avoid that double counting, we don't put it there anymore. Do you see that this is a tetragonal and this is a face-centered tetragonal? Because on the 6 faces, I have the 6 atoms. And you can see that I have marked the 2 atoms A and see what these 2 atoms do as I move this around. So what I have done here, that was one unit. I just copied another one. You can see, just copied another one to the extended to the left and also on the top and on bottom. Right? That's exactly what I've done. You can see where the C is. C was in the face, so the face is being shared by 2 neighbors. And so this is being common on both the neighbors. Fine. Now, and look at the A. Okay. Now you see, do you see? So the C now you see is still, it was on the face, but if I just look it slightly in the corner, the same crystal, instead of looking face on, if I look at diagonal on, then that becomes a body-centered cubic. And as a result, then you can see that therefore this is not a new lattice, because it's an old lattice viewed in a different way. So you shouldn't put it in. One of the amazing things, and that's where I'll end, is that this counting was done before people knew about atoms. Simply based on the fact that, all these crystals, the jewelry people and others, they had been studying this for a long time. You want to give a king a nice diamond so that he gives you a lot of money back. So people knew about crystal planes a lot. And by 1840s, people have already figured out all these answers, 14 type of Bravais lattices. But actually they counted 15. The first person is not Bravais. The first person is Frankenheim. In 1842, he counted 15, just one more. And a few years later, Bravais is, of course, a very famous scientist. He did lots of other things. And Bravais pointed out that 2 of the lattices that Frankenheim said, they are exactly the same. And therefore, Bravais' name remains and Frankenheim is forgotten. You see, just one mistake. And 150 years later here, we are talking about Bravais. Frankenheim gives our sympathy, but doesn't get any prizes. Okay, and let me conclude with this. The Wigner site cell for BCC and cubic lattices. One thing I want to point out, these 14 cells that you saw, these were not necessarily primitive cells. These were the cells that were easiest to deal with. But if you wanted to do primitive cell, then you should do how this has been done. For example, you have a center atom. Look at the right one first, the cubic one. So in the green, center atom, and you can see the neighboring atoms have been connected, and bisected by a plane now. Instead of a line, it has been bisected by a plane. That's the blue transparent, the cube that has been generated. That's the Bravais lattice, that's the primitive cell for this structure. In many cases, for the cubic, it's exactly the same, but for many other systems, you will see, especially for face-centered cubic, it's not the same. For example, in the face-centered cubic, I will show you that Bravais lattice have a volume of factor of 2 off, or factor of 4 off compared to a primitive cell. You will do it in your homework, you'll figure it out. Okay? So let me conclude. So I tried to explain to you that first 5 weeks we'll be talking about 2 basic concepts: number of electrons, and then we'll be talking about the velocity of the electrons in order to calculate current. We're talking about number of electrons, and we've spent some time in talking about different types of materials available, which is fine. You know, we expect gallium arsenide to be different from silicon. We understand that. But we are now also talking about periodicity and structures, and the periodicity and structures are very important, because if there were no periodicity, there is no hope, no matter what computer, of solving the quantum mechanical problem that will give us the number of electrons. So we do it because of convenience, but later on we'll see, even when things are not periodic, many of the conclusions that we reach here will remain essentially the same. That's why we'll spend so much time on the periodic structure. Okay, that's it.